Hello, hello, and welcome back to another video in section 14.2. In this video, I'm introducing the unit tangent vector. We'll talk about some issues with this and then work through a couple examples. Let's get started. So, when we're dealing with derivatives of vector-valued functions, as we know, the derivative of a vector-valued function, right? If this is telling us position, the vector-valued function, then the derivative is telling us velocity, right? And in general, the derivative points in the direction of motion, and the magnitude of the derivative is the speed at which the object moves, or the particle, whatever you want to think of it as, moves along the curve, right? So it's telling us two things. It's telling us direction of motion and speed of motion, right? So if we take the magnitude of r prime, that gives us speed. But in some of our calculations, we'll just want the direction of the tangent vector. And this is also just a useful thing to get, is just the direction of motion. I don't want to know anything about the speed of motion. I just want the direction of it. So if I'm in that sort of situation, what we do is, well, we find a unit vector in the direction of motion. And so what that looks like in terms of vector-valued functions is we're taking the derivative here, that's my r prime of t, and dividing it by the magnitude of the derivative. So again, we're thinking of this as like speed, right? This is what the speed is, and this is scalar valued. Scalar valued. So we're scaling the derivative by 1 over its speed. And remember, the derivative itself, this is a vector. And so this tells us both speed, right? It has information about speed, specifically its magnitude is the speed, and direction. So when we divide through by its speed, what comes out then is just a unit vector in direction of motion. And like I said, this will be useful for us for calculations, as well as just if we want to know just how this, what direction the thing is moving at a point in time. So this is a sort of two-step process to find this unit tangent vector, is what we call this, right? It's a unit length, right? Magnitude of t, because we're doing this, will always be unit length. I'll talk about issues with this in a second, but it will most of the time be unit length. And be in the direction of, and it'll also be tangent to the curve at that point, right? So yeah, what's the issues with this that I keep talking about? Well, what if my object stops moving for a moment? So what if r prime of t, what if my derivative is the zero vector? Well, if that happens, then the magnitude of the derivative at that point will be the zero scalar. Let me maybe change t to, let's say, a particular instant in time. If my derivative comes out to be the zero vector, then the speed at that point is 0. And, well, I can't compute the unit tangent vector, right? If I try and compute this at time value a, I would get r prime of a over magnitude r prime of a, but this is, right, this is 0, so this is undefined, right? We would have an undefined unit tangent vector. And the idea here is if we stop moving, then we have no direction of motion, right? And we can sort of swivel all we want, and our direction of motion can change sort of very radically at points like this. So this is almost like a discontinuity or something with our vector valued function. Let me show you a image to get this across. Well, I'll jump over here first, show you this image to try and get this across, and then I'll go to an interactive figure. So the idea is sometimes we're going to want to put a restriction on our vector valued function. We're going to want to say we just want to consider vector valued functions that aren't 0 anywhere. And we call these things smooth curves. So the key word here is smooth. And what smooth means is that, one, it's differentiable. We want to be able to differentiate this at any point on some interval. And even more than just being differentiable, we want r prime of t to not be the 0 vector. So as long as that doesn't happen, as long as it's not the zero vector anywhere on the interval, then the unit tangent vector is defined over the whole interval, and we have a well-defined direction of motion, right? So like with something like this example that I have here, if we try and find r prime of t, let's find r prime of t. Remember, to differentiate component-wise, we would have, what, 3t squared, 6t, and then here we'd have 3 over 6, or 1/2 t squared. And then if I try and find, let's say, the speed, or let's just try and find the derivative at 0, at t equals 0, I get the 0 vector. And then the speed of the object at that point, derivative of r prime of t, will be the scalar 0, and t of 0 is undefined. So that's a problem, as I've mentioned. That's a problem. It's going to mess up, right? We don't have a well-defined unit tangent vector there. And what this looks like in the curve, at least in this instance, is a cusp. So I'll jump to an interactive figure to kind of try and point this out a little bit more. Here is my curve that we've already described, right? It's this vector equation. And so it comes in below the xy plane, it goes to the origin, and then it comes out from the origin above the xy plane in this sort of fashion. And so we can have r prime of t anywhere except for the origin, right? It's going this way at this point. I can get a little bit closer to the origin. It's moving a little bit slower there. You see the magnitude of my r prime got a little bit less. And finally, so let's try and inch forward to 0. It's getting smaller and smaller, the speed that is, until we eventually get exactly to the origin. So here we are at t equals 0, and we get the 0 vector for our derivative, and hence no unit tangent vector. And as I said, the direction of motion then changes wildly, right? I just increased it by 0.5, and already our direction is completely opposite what our direction was before. So cusps like this are problems, and sometimes we'll want to put a restriction on our curves. We'll just want to consider smooth curves. That way we can think sort of theoretically and avoid this case when the unit tangent vector is undefined. So that's the idea behind smooth curves. All right, so let's go ahead and just work through a couple examples here. Refresh our memory on how to compute derivatives of vector valued functions. And we're going to work on finding unit tangent vector. So this is, again, a multi-step process, so I'll kind of work you through how I find a unit tangent vector. So what we need for the unit tangent vector, remember, let's refresh our memory. The unit tangent vector is r prime of t, so we'll need the derivative of r, and then we'll also need the magnitude of r, the speed. So let's go ahead and get hold of that. So r prime of t here, since I can't write in boldface, right? Notice on the slides I have boldfaced r, that's a vector. Since I can't sort of write that with my hand, I'll put an arrow over it to indicate that it's a vector. You should do the same. 2t, 4, and then 4 over t. All right, cool. And then let's find the magnitude of this thing. So magnitude of r prime of t, this is the square root of each of the components squared added together. So I'll have 4t squared, right? That's 2t squared, plus 16, plus 16 over t squared. So that's my, this is my speed, right? This is a scalar quantity, and it represents the speed of motion. Let's see. I think I'll just leave it like that. And so now we can write the unit tangent vector t of little t is r prime of t over this. So I could write it as 1 over square root 4t squared plus 16 plus 16 over t squared. I could write it like that times my vector 2t, 4 over t. The other thing I can do is if I recognize that some things are going to cancel, I can bring this scalar through to each one of the components. So I could also write it like this. we'll say, so it'll be 2t over square root 4t squared plus 16 over t squared, comma, 4 over square root dot dot dot, and then 4 over t square root dot 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 dot. So I could also write it like this. And like I said, if there's some cancellation going on, if I can recognize that some cancellation is going to go on, maybe I want to bring that through. So here is an expression now for our unit tangent vector, which just tells me the direction of motion at each point. I've sort of removed the speed of motion from it. Let's do the same thing, or actually let's look at an example of that one real quick. I have that one graphed. So let's jump to that one. Here we go. Here's t squared 4t 4 natural log of t. So I can, let's say, pick t equal 2. I can graph, or I can plot my derivative vector, right, my tangent vector. Of course, it's going in the direction of motion, and it's carrying information about speed, right? Its magnitude is the speed of motion. And then if I divide through by that magnitude to force it to have unit length, what I get is just the direction of motion. So just this little green arrow here is telling me direction of motion. And I can now change my t value. I can recover what the direction of motion is at any t value that I want, right? So it just forces it to have unit length. Notice that the unit tangent vector and the tangent vector are parallel to each other at all points. That's always going to be something that happens. They'll always be parallel to each other because they have the same direction. But the unit tangent vector will always have unit length. All right, let's do one more example here. We'll find the unit tangent vector. So let's see, I'll find r prime of t first. Derivative of 10, that's a constant, is 0. 3 cosine t here, so that'll be what, minus 3 sine t. And then I have 3 sine t here, so that'll be 3 cosine of t. Cool, let's go ahead and find the speed of this thing. So magnitude of r prime of t. Not a vector, it's a scalar. It's square root of the sum of each of the components squared. So what'll I have here? I'll have 9 sine squared t plus 9 cosine squared t. And here we'll have some cancellation, or rather an identity to use, right? We have sine squared plus cosine squared, that's 1. So we just get 9 here in the middle. So this is square root of 9, which is just 3. So isn't that nice? This vector valued function, right, if we think of this like an object moving along this curve, it has speed 3 at all times. So this is easy for now computing the unit tangent vector t, which is, of course, r prime of t over the magnitude of r prime of t over the speed. And so I'm just going to divide through everything by 3. So I'll still have a 0 here. Here I'll have minus sine t. And here I'll have cosine of t. And that's pretty nice. So now we have the direction of motion for this object at any point on the curve, or rather from t between 0 and 2 pi. All right, that's it for this video. I'll see you next time.